topics I like. And so today I'll be talking a bit more about some of the simulation aspects. How do we solve some equation in the computer, and then do some exercises again in the afternoon. So just program for the week. Today it's going to be numerical method for gravity, and then this afternoon we'll be running cosmological simulation and looking at some results. So yesterday you played a bit with the code, so everybody could start. It was not a big simulation, but you evolved the tools, so now we can do something a bit more complicated this afternoon. Then tomorrow we'll talk about simulating gas and turbulence, and I'm sure you'll be interested. Good. Any questions from yesterday before? No. Question from me. So this is the yeah.
I have a question.
Yeah.
Yesterday we saw the how is kind of physical theoretical physics and observational physics, and
Yes.
they differ. So in stellar physics there is this parameter called the extinction that shifts or numbers along one on the linear. And is there a parameter that can shift or value the whole constant in cosmology? So we have a precise number, but not around the exact number.
Yeah. So that's a good question. So some of these measurements, especially the measurements from the supernova 1A, they depend on. So we assume that all the supernova have the same brightness. And then, because we know how bright something is, if we see it's fainter, then it has to be much further away. We can use that information. Now, the question is, here, the key assumption is that all of the supernovae behave exactly the same. If they don't, then you have a problem. Then you're not sure exactly how bright something is. And so then, there are two problems. One is we don't know, in theory, how supernova 1A work. So we don't have a full explanation for that. So we have to do it with observations. And in observations, we see that there are some small shifts, but we believe we can correct for it. But that's an assumption. Then the other problem we can have is that we don't have any supernova 1A very close by. So we need to. So what we do first is that in the Milky Way, in our galaxy, we measure Cepheids. You know what Cepheids are? So they are these variable stars that also have relationship between brightness and period. Right, so then we can measure that distance, and then there are a few other galaxies. I think it's only 3, where we have Cepheids and supernova 1A. So then what you can say is you can calibrate the supernova 1A distance on the Cepheids, and then you can use the 1A until very, very far. But there is a critical bit here that there are only 3 galaxies where we have 1A and Cepheids. So we need more data there because that's a big error bar possible. So there are still some things that we may have to understand. Good. All right. Let's go on with today's program. So I showed you this one yesterday. I'll show it again in the background more for fun. So in terms of simulations involving just the evolution of gravity, sort of old school simulation here. And so what we're going to be talking about today is not directly that, but still some of the calculations, some of the methods that are used here were already used 65 years ago or so, are still relevant today. I mean, the gravity is the same, and some of the algorithms haven't really changed. And so that's what we want to explore a bit today. Now, here's a question for you. So we are solving gravity. So okay, so yesterday I mentioned a bit about Einstein, gravity, and general relativity, and everything. Now, first question is, do we ever need that? Do we need general relativity for any of the things we want to do? Or ever for anything? Okay, so any guess? I guess I'm asking a question, so you probably guess the answer. The answer is generally no. It really, there are very, very few cases where we actually need to use general relativity and not just Newtonian gravity, right? I mean, Newtonian gravity is one of the limits of general relativity. You only need general relativity if you are doing calculations if things are going very, very fast, and that means fast compared to the speed of light, or if there's a very strong gravitational field Yeah, that's the problem, right? So if you have a reason why you could cancel some of the dimensions, that would happen. Right? So if you know that your problem will have no velocity out of the z direction, for instance, you could kill one dimension. But that's not true. Things have to move in all 3 directions, all 6 directions. Right? But we have to do something, okay? So we'll have to find a way, and there's a way out. So how do we? Any suggestions? So I mentioned 3 things yesterday that physicists also 2 things that physicists always do yesterday. Yes. Can we make that into a harmonic oscillator?
Maybe make it as a spherical coordinates. I don't know. I'm just thinking about just 2 dimensions.
Yeah. So
make it simple.
So we can of course make it simpler, yes, but that's not what we want. We want the full thing. But yes, that's where we are going. We're almost there. So we can't really make it harmonic oscillator because we would need high order derivatives, right? It's only first order, so we don't have any things that we would need second order derivatives. That's another trick people use. So then there are 2 more tricks that people usually use.
Guessing.
Sorry?
Guessing.
Yes, we're gonna guess something. We're gonna guess something in a minute. Fourier transform will help. Where do we Fourier transform? What do we Fourier transform here? So we're gonna in a minute. We're not gonna start with that, but Fourier transform is gonna help for this one, for the second equation. So then the 2 other tricks that we usually use is either perturbation theory, where you say the small changes are small, so I can cancel some terms, but here the changes are not small. That's exactly why we decided yesterday we have to stop and do simulations. And then Fourier transform with the other. None of them directly work here. So indeed we'll have to guess something. Right? So we have to guess, not quite guess. We have to do the last technique that you use when you're sort of desperate and you have no other solution. You sort of guess a good shape for the solution. So what we can do is I will try to simplify f in a way that I can solve this problem in a sensible way. So what I can do is I can guess that f is not a continuous function. It's made of this Dirac distribution. You know what a Dirac distribution is? That's a function of 0 everywhere and it goes to some name. So if I make my f to be made of a large number and of it's 0 everywhere and then there's a spike and there's another spike somewhere. And then okay, so if I take a Dirac, it's obviously not working, but I can make it just slightly not quite 0, not quite infinity thin. Then, if I have enough of these ends, I have a sort of a good approximation of f. Right? I just have, because spikes everywhere, and then if the spikes are just broad enough, then I can have my f be almost approximated like this. So if I choose n large enough, I can approximate any f, or I can approximate any function with this trick. Now the question is, does it actually help? So the larger number of these 6-dimensional directions, the better I approximate. And then what we're going to call this, we're going to call this each of these Dirac things a particle or a body. So it's like an n-body problem now. I have n of these infinitely slim point mass type things. And then if you want to get some more background about this, is what we call a Monte Carlo approach. So Monte Carlo is the city of Monaco in south of France, where there are lots of casinos. So there is a reason why it's called a Monte Carlo approach, because you're doing this, so it's a random thing, right? It's like playing a casino game. Maybe you win or not. So what we're doing here is that we are taking f, and we are drawing random points to say, I don't have the full f, I only have f at some random position x and v. And so this is a very general way you can solve lots of problems, where by doing some random guesses. And then you can show, and I'm not going to go into that it goes to the correct solution. It doesn't go to the correct solution very, very fast, but it goes to the correct solution. So you will need a lot of ends, a lot of these particles and bodies to get to the correct solution. But at least it's tractable. And what we mean by that is that if I have 4 times more particles, then it gets twice as accurate. It's square root, scale to the square root. So if I have 100 times more particle, it's 10 times more precise and so on. So that's why I need really, really large ends, because I want the convergence is relatively slow. Okay, so now if I have this, assumption about what my f looks like. I go into my equation and I just take the derivative, the df by dt, the df by dx, the df by dv, and I replace all of the terms. I'm left with, and I can rewrite this as 3 separate equations, right? Now, the nice thing is that they're not coupled with x and v anymore. I get 3 separate equations. The first one just tells me that the position changed like the velocity, which that's not a very interesting equation. We already knew that before we started, but that's just one of them. Second one is that the acceleration is due to the just the gradient of the potential. Again, we knew that from Newtonian dynamics. And the last one just tells us how to calculate the forces between the particles. This could also be replaced by the Poisson equation I had before. So this is, it comes out, right? So this is if you ask you, well, here's a set of planets, calculate how they move. This is what you would write down. But also, it comes out naturally if we assume something about f and we make this approximation, which gives us a more formal context about why this should work. And that's formally called the n-body problem. And then if you only have 3, then it's a 3-body problem, and so on. And so this is one n-body approximation to the Vlasov-Poisson system. Maybe some comments on this. So this is now a 3D problem. You only have to solve in superposition. So that's a lot simpler. We killed off 3 dimensions, which is what we wanted. But instead of having one equation, we now have 3 times n equations. I mean, 2 of them are pretty boring because they're just position equal velocity and acceleration, but we still have 3 times n coupled equations, not just one equation. And then one final thing is that basically, apart from this couple of tests that people have done simulating f directly, this is what every single simulation does. This approximation is the choice everybody has made, and because it's basically the only way we can do anything. This was good because it means a lot of people are working with it. But it could also be bad, because if there is something fundamentally not good, then everybody is doing the same mistake. Apparently there's not, it's not a problem, but just philosophically, if you have different ways of solving the same equation and everybody finds the same solution, that's great. If you only have one way of solving an equation, everybody finds the same solution, that's good, but there's only one way, so maybe, maybe it's not a surprise that everybody finds the same answer. Okay, now I mentioned before, it didn't fit in memory. So let's try whether now that calculator, if we do this, can we now put this problem into a computer? So I showed you this simulation before yesterday, which was in the other direction, which is on this Euclid flagship simulation, which had 8 times 10 to the 12 particles. Now, they use a very, very efficient code that only uses 28 bytes. So that's about 7 numbers per particle in the code. And so that means I only need 200 terabytes of RAM. So that is a lot, but it's not untractable. As mentioned before, the biggest computer had 4 something petabytes, so that's 20 times more. So here, you only need a friend that has access to a computer which is only 20 times smaller than the biggest. Still difficult, but it's possible. And clearly people have done that.
But this is only approachable with clusters.
Yes.
I imagine.
Yes.
Yeah. How come one to manage to fit all the information of a particle in 28 bytes?
But what do you need, right? You need position, x, y, z, velocities, x, y, z. That's it. What else do you need? So that's even 4 byte extra, which I forgot what they use it for.
Right. So that's just the information of one particle.
Yeah.
When one is already running the code,
yeah,
and he's computing all the equations,
yeah,
doesn't it increase the RAM?
Yeah, so you have extra needs. So this is just for the particles. It's true that we'll see in a minute how we do some algorithms.
So just for the initial conditions.
That is what for the particles. So there will be extra things in the code. For instance, you need to store the acceleration. You don't need to keep it forever. You can, and then you can, right? So there are a few extra things that you may need temporarily, or that are not change with the number of particles. But yes, it's mostly that part. So there'll be a bit more than 200, but that's what it is. So that is now sort of doable. Clearly, people have done it. Okay, maybe a question for you. So some people already asked yesterday in the exercises what the mass of the particles was in these halos we were simulating. So in these simulations people do, the particles have a mass, somewhere between 10 to the 4 or 10 to the 10 solar masses per particle in this body in the simulation. It depends a bit on what region of the universe you want to simulate, the detail level of details, and so on. Okay, so if you ask particle physicists what is the dark matter particle, they will tell you, well, it's something that has like a 1 GeV, giga-electron volt mass, which if I turn this into astronomy units, this is 10 to the minus 57 solar masses. Okay, so okay, I have a number here which is say 10 to the 6. This one is 10 to the minus 57. So I'm 63 orders of magnitude away from simulating dark matter. Why is what I just told you correct? Why can we do simulations using particles that are 63 orders of magnitude away from reality?
Maybe it's not the mass we need, maybe it's the potential. Well, I don't know, just guessing me.
Yeah? No.
If they're in the same scale, it's, I don't know, really the same.
Well, you could say if I want to simulate dark matter, I have to make sure every particle in dark matter is simulated correctly. So then I'm 60 orders of magnitude away from doing that.
Because I need to measure a single body, but in effect of a group of particles.
Yeah, so that's part of the idea. So indeed. So there are some particles, whatever dark matter particle you like to choose, say the normal cold dark matter wind type thing or any other particle. And then physics tells us that if there are enough of these particles, we can treat it as a fluid. It's the same when we think about water or gas. You don't think about every single atom in the air. You can treat it using the Euler equations. You can treat the evolution of the gas using a set of equations independently of the fact that the gas is made of individual atoms. So I have physics telling me that I can go from individual particles to F. And then I made a choice in my simulation that I'm going to use F and represent F with particles. But there's no direct connection between those two sets of particles. If I was simulating F directly without particles, or just using F on the grid, we would not even have that debate at all. Because there is no concept of a particle there anymore. There's only this particle, and then F on the grid. And then we don't have that discussion. Okay, so there's no need to have a confusion between the real dark matter particle and the simulation dark matter particle. You're confused.
Yeah. So the thing is, we treat it like a fluid, but at the same time, no.
So we treat it as a fluid, and then we say I'm going to approximate that fluid using another set of particles, which is unrelated to the real particle of the universe.
So computationally, we are not treating dark matter as a particle, but as a fluid.
We're treating it as a fluid, right? Because there are so many of them that we can treat it as a fluid. And then I use another set of particles to solve that fluid equation.
Wait, again, please.
So I'm treating it as a fluid because there are so many particles. Like if I wanted to simulate the gas in this room, I can treat it as a fluid. I don't have to track every single atom of gas. Okay? So this is just statistical physics. And then now I'm in a computer and I decide I don't know how to solve this equation, so I'm going to solve it using particles. But these particles have nothing to do with the real world.
So if I get it right,
Yeah.
one, you run this simulation
Yeah.
with a fluid in it,
Yeah.
which will behave as dark matter. And then
Yeah.
when you finish the simulation, you get out like the fluid, then solve it with a function.
Yep.
To see the distribution of dark matter.
Yes. So F tells me the distribution of particle, tells me how many particles there are at a given position in velocity. Of real particles.
Right.
So if I know F, I know everything, that's all I want to know.
Okay.
But then I used to to solve f, I use another set of particles. And at the end of my calculation, yes, my results, snapshots of the calculation will have a bunch of particles, but from that I can reconstruct f.
Is it like to treat f as a density function to
This is
the
a
simulation,
function, yes,
and then convert it to the discrete function?
correct.
Right. Seems legit.
And how is going with the errors? It's not making like too much errors, or?
Well, so this numerical method gets closer and closer to the real solution as I make my n bigger, right? Because I have more of these direct distributions, and because we don't have time to go into the details, but as I said before, it goes to the square root of n. So if I have 100 times more particles, it gets 10 times more precise. Okay, how about stars? So stars, you can say, they are not quite like Darwin particles. They're not 10 to the minus 57 solar masses. They are 1 solar mass. So they are sort of on the limits of what should we do with them. Should we treat them individually, or is there a fluid of stars? So depending on what you want to do, if you're doing very large scale simulation and you don't have a lot of detail, maybe you can also treat the stars as a fluid. Say there's a bit of star fluid and then use the same approximation. Or if you're interested in simulating, say, the globular cluster or the solar system, clearly in the solar system the sun is not a fluid. So you need to simulate every single star and planet individually. Then it depends a bit on the science case of what you want to do, depending on how you want to treat stars and then other things like black holes. Okay, so we've seen almost this written before. So how do we do the equality algorithm? So I have a starting point. You mentioned initial conditions before. So I have initial conditions, I have a starting point. I choose a small time step, small jump in time. And then what I'm going to do is that I'm going to calculate the accelerations, update the velocities, update the positions using my small time step. And I do this again and again and again until I reach the end of time. Or the present day, or whatever you want to stop. That seems very easy. So here's an example. I think we can do this simulation this afternoon. Sorry. I thought it was a movie, but it's not. So yeah, so this afternoon we're going to be running a small cosmological simulation like that. Oh, it is a movie. With some specific cosmological model, and I don't know if the network will work. Yeah, so there you go. So we start very uniform universe, right? Think of cosmic matter background. And again, here I've taken out the expansion, right? In principle, the whole universe expands, but to make the movie, we take out the expansion so we can only see what is happening on top of that. And you should see filaments forming and so on. It's a long process. So you can see gravity making these filaments and halos collapse, as we have seen in some of the other movies yesterday. So, like this. All right. So I guess we have already almost touched upon that. So what are the requirements? So yes.
Go to reduce to 3D.
The other way around. This one.
No,
The movie.
yes. How far from the edge do we be sure that the exceptions?
Good question.
Right.
What do we do with the edge?
Oh, that's the question.
Okay. What do you think we do with the edge? So that's my question now. What would you do with the edge?
The idea is to simulate that the edge also has something like next to it, so that it behaves somehow like the rest of the particles. But I don't know how to maybe to set that on the potential on the edges
Yes, there was another suggestion here. It's,
like that. A repelling particle.
you have a repelling force, yes. There's another suggestion here, maybe?
Maybe if one particle is closer to one side of the square,
Mhm.
you put it on the other side.
Correct. So that's the best solution. So if you do, okay, so all right, so you could put an edge, but then what you have there is that you are saying there's an edge of the universe, right? So that would be, well, unless you believe there's an edge of the universe, or there is something you want to simulate, then you have a problem. What you can do instead is to say, I can make it periodic. So if a particle goes out on one side, it comes back on the other side. And because it's periodic, means there is no edge, it just goes to infinity and in all directions. And that makes a problem that solves that question, what happens at the edge. Okay? That's the normal way of doing things. The other thing you could do is you could say, I'm going to make it expand completely, and then, of course, it will be a bit weird at the edge, but you could say, I know how far a particle can move over the whole history of the universe, so I'm going to cut out the outer bit of my simulation and say, put it in the bin, and never look at it. But that's a bit more wasteful, because you're like wasting. So if your simulation is really, really big, then the edge is very small, so then it's a small overhead. But if you do a small simulation, that's something good idea. So we call this periodic boundary conditions. So boundary conditions is what happens at the edge, and then we do periodic to simulate the fact that it's essentially infinite universe in size.
So that means that a particle on the, for example, left edge is actually interacting with a particle on the.
Correct. So particle which is on this side here receives gravity from these guys on left, but also from these particles on the other side. And if it moves out, it comes back on the other side. It's like a like backward, right? So the what? Exactly, or like a torus or something like that. Yeah. Okay. So we want small particles still because we want to have more. The more particles I have, the more precise my solution is, as I said before. But we also want to have a large section of the universe because then it's more representative. So consequently, we want a large value n. We are greedy people. We want to make this the biggest possible simulation, the best possible results. We want a large number n. Okay, so now there are three main questions that remain. Let's go from the bottom up. So how do we make initial conditions? What is the starting point? Right. So we'll talk about this at the end today. But we talked about yesterday how we have the fluctuation in the microwave background, just small fluctuation. So we sort of know physically what the starting point should be. Right? I can probably make something that looks like the cosmic microwave background, and then calculate from there. So maybe initial condition is not bad of a problem. Second problem, how do I choose my dt? I said before, we're going to choose a small time step, dt, and we're going to move my system forward. Now, if I make my that delta t very large, say if I take 1 billion years, then I'm only going to do 13 steps in the history of the universe. So that's really not going to be very precise. If I make it 1 year, then I have to do 13 billion steps, and then that's going to take way, way, way too long for my simulation to ever finish. So I need to find something in between, and I need to find a good reason and a good way of choosing my value of dt. We're going to look at this a bit later. And then the main question is, how do we calculate gravity, right? So we said I have to take each particle and calculate all of the forces. That was in my n-body algorithm a couple of slides ago. How do I do this? And that's the key question, especially when n is very large. And then the other challenge is sort of what you mentioned before, is that typically these big calculations, they don't fit on a single computer. They will fit on a cluster. So here's an example, which is an image of the Supermook machine in Germany, where we've done some calculation. So, it's 20 meters by 20 meters, so 25 meters by 25 meters. Each of these here is what we call a rack, and in there you have probably like machines like that. You have about 2 of these every 5 centimeters, and they go from the bottom to the ceiling. And then all of these are going connected via cables on the top. right? So it's a lot of CPUs. I think this machine here has 250,000 CPUs, right? So one of these maybe two. And so the challenge, and we're not going to be covering this part here, but the challenge is not just that you have to write software that can run on one machine, but you also have to write software that can run on many machines and then communicate and talk via the cables to the other machines, right? So that is not very standard software. You have to write specialized software that can talk to other computers very efficiently at the same time. And so that, especially if you make N very big, this is the only solution. You have to go to a computing cluster. And the biggest machine in the world now are about 10 times bigger than this. So you have maybe 4 million CPUs or something in the machine.
It is crazy to think if maybe using parallel coding will be, right?
That is parallel coding that you have to do.
Okay.
So you have to use parallel coding, so because you have all of the CPUs working in parallel. But when you write parallel coding on one machine, that's relatively easy because you can see the whole memory. But here you have some of the particles you are using are in a different computer. So you can calculate the position of or the force coming from another particle, but that particle is in a different computer. So you have to sort of ask it over the internet. It's not the internet, but some communication. Tell me what the position of this particle here is, so I can calculate the forces. You have to do this across the whole system. So you have to be, it can get very complicated very quickly. Please.
Can we have a simulation integrating from forward to back,
Good question.
giving the initial condition like nowadays?
Yeah. Would that work? What do you think? Yeah, so there's nothing stopping us from running a simulation. So the algorithm I have, I can take my dt and I can just make it minus dt and go back in time. So you could say, what I can do is I can take the current universe as it is nowadays, I reverse the sign of time, and that tells me what's the background universe should be. Yes, it works. There are two problems with this. One is we don't have data which is accurate enough, because you need a lot of positioning 3D quite precisely to do this. And then the other problem is that, well, actually that would be the main problem, is that we have very, very good data very close to us, but then the further away you go, the more difficult it is to do measurements. And so then it becomes much more difficult. The other thing you could say, well, I can do the simulation once forward, and then I change the time, and I go back, and I should recover the same thing. That doesn't work either because we do approximations all the way, so and then they don't necessarily add up in the same way when you go back. So you don't necessarily always get the same answer. But yes, you can reverse the sign of time if you want to see what happens. Okay, so the main difficulty is calculating the forces. So we need to calculate the effect that every particle I has on every other particle j in my entire calculation. Okay? So if I have 10,000 particles, I need to calculate 10,000 times 10,000 interactions. So that's 100 million. If I have 10 to the 10 particles, I need to calculate 10 to the 10 times 10 to the 10. That's 10 to the 20 interactions. It's a very large number. So we need n squared interaction, or n squared of 2, because it's symmetric, but that doesn't really help save you much, so the factor of 2, not the factor of a lot. So is this even possible? And I guess the answer is already no, otherwise I wouldn't ask you about it. So let's just check what that would be with a real life example. So I want all of the pairs of particles at every time step. So let's take this simulation I mentioned before, the one that just fits in memory, which had 10 to the 12 particles. So in their case, they had about 11,000 time step, these delta T jumps, so about 1 million years. So I have to do 10 to the 12 times 10 to the 12 in calculation at every time step, and then I have 10,000 time steps, so that's about 10 to the 28 gravity interactions that I have to calculate. Okay, but I have a big computer, so maybe that's okay. Now, if I take the biggest computer in the world, called Frontier, it can do 1.1 exaflop. I guess that's a unit you have probably never heard of before. So a flop means floating point operation. So it means one calculation. Typically it means one multiplication in the computer. So if you take two numbers, just multiply them. The time that takes, so flops, that would be floating point operation per second. So that means how many multiplications can you do per second? Right? So if your computer says 2 gigahertz, it can do 2 giga operations per second, so 2 billion operations per second. That's what this frequency means. So if your computer is 2 gigahertz, which is a normal frequency of a laptop or a computer, it can do 2 billion multiplication per second. So it has 2 billion flops. It has a 2 gigaflop performance. Okay? So this one has 10 to the 18, so that's an X, so you have, so before we have tera for memory, we have petabyte. So giga is 10 to the 9, tera is 10 to the 12, beta is 10 to the 15, and exa is 10 to the 18. So this one has 10 to the 18 operations per second. So you can do 10 to the 18 multiplications per second, provided you're writing perfect code. Perfect code, that's what you can do. One gravity calculation between two particles costs you 22 math operations, on average. So I have 10 to the 22 interactions times 22 this, and if I divide that, that tells me how many seconds I'm going to finish. That's 6,300 years. Okay. So if you have very good friends that lend you this computer to play with, they need to give you the computer for 6,300 years for you to finish the calculation. So again, that's not going to happen. It fits in memory. That's already the first step. The previous one, but it didn't even fit in memory, but it takes way, way too long. In practice, that calculation, they did it in about 1 month. Right? So clearly, a much better way of doing it. So we need to be more clever. So this is just a plot from a relatively recent review, where we show, so these are different years, and then the number of particles that people have in their calculation. Now the red points are when people do direct calculation. So they calculate every single pair, like in this very naive, very inefficient way. And then maybe the biggest calculation these days have about a few million particles. But people that are doing more clever technique that we're going to discuss in a minute have calculations which are much, much bigger. So this is 4 or 5 orders of magnitude larger. And the only way you can do this is by using extra approximation in calculation. You can't just calculate all of the pairs. That's way, way too expensive. So there are different codes in the literature. We're going to I'm not going to go into the details of everything, but there are 2 main categories, and we'll discuss some of the techniques after the coffee. But they're mostly codes that use a mesh and code that use a tree, and I'm going to define this a bit later. The one we use in the exercise today uses a tree, but they're all those kinds. They all work very well, just doing things in a different way. And then maybe the main thing is, if you have a problem, how do we choose a code? Right? That's often a question. People come to me and say, "Oh, how do I want to do this simulation? Which of these many software should I be using?" Right? Sorry? Well, so to me, it depends a bit on what you exactly want to do. There's not always one answer. Of course, I like people to use micro, but it's not always the best solution to whatever problem you want to do. So it depends, for instance, which language it's written in. So if you're going to if you have to modify the code and it's written in a language you don't speak, that's not very practical for you. So you're going to be wasting a lot of time. Maybe it's not running on the kind of machine you have access to. For instance, some computers only have these GPUs, these graphic cards, and some of these codes don't work on graphic cards, or the other way around. So maybe or maybe maybe you're doing different code if you're interested in doing cosmology or interested in doing planets or star formations. Right? It's not always the same code that does the best at everything. And it also depends if there's some of these codes, for instance, the one that did this big gravity calculation, it can only do gravity. It's specialized, it's really, really good at this, but it's the only thing you can do. So if you're interested in doing star formation or something else, that's not the right code. So you see how easy it is to extend to more of the physics that you are interested in. So, any questions here before we go deep on numerics? No? Shall we take a quick coffee break? Let's take a 5-minute break.
Puedo responder.
What is the register? So what we do is that we disable it for time. Now, I could put instead of register, I could have time on top of that. We will but people like to describe time as much as register because it's something that's registered further back in time. So it's easier for present in this state, or instead of 40 times, instead of 6 million years of the Big Bang side. So we convert redshift to time. Sorry, time to redshift. It doesn't mean it's moving far away from it. It's just conversion from time to redshift. It's more friendly.
Vale, que con los bordes de la simulación menos se propone ya digamos que la configuración del borde será el otro borde para que no se pierda un día. No tiene bordes como todo. Sí, y yo le pregunto además si entonces una partícula que está en este borde interactúa con la partícula que está en este otro borde. Me dice que sí. Todas interactúan con todos. Para que vean la consistencia de la función. Y que si la partícula está buena, entonces aparece. Pero esta partícula ya está
Entonces, la pregunta es, si para un disco estábamos con eso de esa la estamos poniendo masas de una,
no, yo solo
ahora las que
si está en este borde, sé que se hace, pero listo.
y con estrellas tan en cuerpo, por ejemplo, lo determina que la masa de una partícula yo creo que me atrevería a decir aproximadamente de 10 a las 7. No tengo ni idea, solamente yo creo que lo tengo un café. ¿Ya? Entonces, el asunto es ese. Si uno pone estrellas sobre las estrellas, en una masiva, de arriba, una de cada vez más grande, perdón, por el final no, galaxias escalares, pues de un plasma no puede eso. Ese plasma no es lámpara, es el nombre original. Exactamente. Pero ya habíamos hablado de eso. Si nos empiezan a mirar cómo están los códigos y cómo corre, pues a ver qué. Esta manera. Al menos no antes de jueves. Ok. Pues no, por eso, no antes del jueves, podría ser el jueves o el viernes. El viernes en la mañana estamos acá. Pero como están los códigos, ya sabes, ¿se acuerdan que vamos a ver esto como una milla casi? ¿Cómo están los códigos?
Sí,
Usted sabe que correr, cómo corren, qué corren.
es un programa. Entonces,
Obvio que no es un programa,
no, pero eso no es un programa como es un programa.
es un paquete, sí.
Ajá. Ajá, entonces, pues sí, yo sé cómo correr, sé cómo más o menos que necesito
Ok, correr para el
que correctamente.
comparar el que con un potencial que corre. ¿Y cuánta memoria requiere? Ay, pues puta, no.
O como 40 cores, pues como idealmente. Sí.
Bien, por eso, a ver, se me está con 72.
72 cores con 60.
72 coros con básicamente un cigarro.
Sí. Pero yo dije, era 60. Pero sí, es demasiado.
Por eso no, mira, no sé cómo se acomoda, pues, es lo que hay, el tema de la escuela como
Sí. Y sería para correr que máquina ustedes a la
pero antes de la una, pues con las cosas. Convenemos un rato, antes de esto que la tarea a poder tener la respuesta que
muchas veces
lo aprendas con
como comprobante
no, pero de hecho les tengo que mandar el correo, pero me pasó que se explicaba muy bien. Paso a saludar, sí, claro. De verdad, no les digo. La simulación se está haciendo la inclusión igualitaria de los dos idiomas en un curso. Gravedad. Gravedad. Es como cuando vos echas a un agua y las burbujas se forman y vos ves que se forman en las burbujas y hay partes donde no hay burbujas y hay partes donde hay más. Una de las burbujas. Eso es no muy material, es una potencia superficial. Funcional a esa escala es muy parecido a cómo funciona el cómputo de la expansión del universo y la gravedad. Pero eso es una regla completamente natural la gravitacional produce perturbaciones permanentes. Las perturbaciones gravitacionales no solamente son radiales, para las direcciones. Cuando resuelve el problema que ya estamos dando la ecuación de las perturbaciones gravitacionales, algunas perturbaciones apuntan todas hacia un centro. Hay otras que son bidimensionales y forman de la misma manera que una espuma, una de las perturbaciones producen en el universo. Los cubos de esa relativa son
Good. Let's resume. Okay, so where have we left the situation? So the situation was we have a calculation which we can probably put in a computer, probably fits in memory, but it's very expensive. It takes too long to calculate all of the interaction between the particles. Okay. So now what we're going to do is I'm going to go through 3 ways we can simplify the problem and actually make it a solvable problem. We can finish the calculation in a reasonable amount of time. So the first one is called the particle mesh method. And you mentioned Fourier transform earlier, so you're going to be happy. We need to do some Fourier transforms. So what we want to do, so if you forget about the particles for just 1 second, what we actually want to do is we're going to solve something like this equation, so that the Poisson equation, but using Green's function. So what I'm trying to solve is just the interaction between every particle, but I can write this as Poisson equation. So what I can do, I have my particles, I can put them on a grid, and I can sort of have a density, I can have a number of particles per grid cell, and I have a density field, and then I can solve my for my forces using Fourier transform. Let's look at this in practice. So if I go in Fourier space, my nada square for the Poisson equation becomes just a multiplication. So it's a lot simpler. I don't have to do any derivatives anymore. I pay the cost of doing the Fourier transform, then I multiply, and then do the inverse Fourier transform, and I'll have my all of my forces on my grid. Okay. And in the case of gravity, this here is just 1 over k, so that's fairly easy, but you could also be solving for differential equations. So here we're doing Poisson equation, which is very simple, but if you had a theory of gravity where it's not Newton's equation, but something else, a bit different, that technique might also work. So, as I said, we Fourier transform the density to get rho hat. We multiply with the grid function, which is 1 over k, to get psi hat, the potential in Fourier space, and then Fourier transform back to go back to the real potential. And once I have the potential, then acceleration is just taking the derivative. Yes?
What does the K stand for?
Oh, the wave number in Fourier space.
The wave number?
The wave, yes, the wave number. Does that make sense? You know what I mean?
I know what you mean in mathematical terms, but I don't get it in physical terms.
Well, me neither.
All right.
So it's like a different wavelength, right? So the first one would be the size of the box, then you have 2 pi over the length. These are if you think about Fourier space, what you're doing is you're trying to decompose the density field into a sum of sine waves. Right? And each k corresponds to a sine wave with the first wave goes to the full box, one that does 2 oscillations, one that does 3 oscillations.
But so in that case, you have to make this multiplication by every k in the spectrum that gets from the Fourier transform.
No, because I only care, yes, but for each k, I have one multiplication. Yes.
All right. So one just have to make one Fourier transform.
Correct?
In this case, for the Green function and the density function.
Well, the Green function we know that's 1 over k, so we don't have to. We can Fourier transform it on pen and paper once forever.
All right, so it's
But it's
just
only for that. We need to transform this, multiply by that, which we know, and then Fourier transform back.
all right. So it's just one Fourier transform to function for all the simulation,
Yeah, what for every
for every step.
step?
This is in the
Yes.
simulation,
Yes.
and then it is just multiplied by every k.
Correct.
By the Fourier transform, the row.
Correct.
Right.
Right. So what we do is that we have a grid. We take the particle, we put them on the grid. So if I say what the simplest thing I can do is just to say, okay, how many particles are in this grid, and then the density in that cell here would be just the number of particles times their mass divided by the volume. And then I can construct a density field, and that's the simplest thing I can do. I can also try to be a bit more clever and say, oh, my particle, they should not just be an infinitely small point mass. I can give it some sort of size and make them overlap into a bit more grid cells. It makes things a bit smoother, but these are slightly detailed. But the idea is that I construct a density grid, and I move to Fourier space, I solve in K space, and I come back. Now, how is that better? Are you familiar with this O of n notation? Okay, so that's what we call, it's a big O notation. What it means is if I give you a problem of a given size, how does the number of operations scale with that number? So if you have something that scales, so if I have, say I have a problem with 10 particles and a problem with 20 particles, if it's O of n, it means it's going to get twice as bad when I go from 10 to 20. If it's n squared, it's going to be 10, and it's going to multiply by 4. If it's O of n cubed, it goes with the cube of the number of particles and so on. So you want to keep this as small as possible. So the normal algorithm where we interact everybody with everybody is n squared, because we have to calculate for every particle, every other interaction. So you have n squared operations. Here the Fourier transform actually goes as n log n. And that's a much, much smaller number than n squared, which means we can actually solve this very quickly. So I compute the density on the mesh, so for each particle I put them on the mesh where they are, so then that gives me a grid of the density field. Compute a Fourier transform, multiply by 1 over k, compute the inverse Fourier transform, and then I can just get the forces for the particles, and I can move ahead in time and start again. Okay? That's a different smile. Okay, so why is it that good? Well, it's fast, it's simple. If you do it in Python, especially for something, you can use the NumPy Fourier transform calculation. You don't have to do it yourself. You can write the whole thing in about 30 lines of Python. And for some version, if you're interested in doing other theories, it's actually relatively easy to do because you just have to change this 1 over k to whatever other formula you could have for your changing rate. So that's the good side. The bad side is that I need if I want to be very precise in my gravity forces, I need to have a very, very, very fine mesh. Otherwise, the scale at which I can solve gravity is given by the number of grid points I have. Make sense? So I need a lot of grid points. So I need to do a really, really big Fourier transform. And so now I'm back to having my problem where I don't have a problem because I have too many particles. I have a problem because my Fourier transform is really on a really, really big grid. If I want high.
In this case, the resolution of the simulation is limited by, I guess, the Nyquist's theorem.
That's correct.
Right. So one must need like double the amount of particles in order to get half the resolution.
So you have those. So you have this aspect. So one is how well can you create a density field on the grid? So you need a lot of particles, but also if you only have like a grid of 4 by 4 by 4, your gravity is not going to be very accurate. You need a really, really high, a large grid to have different value of the potential everywhere. And then that becomes expensive again. So this is what calculation maybe 30 years ago were doing. That works very well because it's very easy and it's very effective. Okay, let's just start this one already. So then people said, well, I have this problem that if things are very close, right? If particles are in the same cell, they receive the same gravity because the gravity is just given on the side to the scale of the grid, not anything else. So they are in the same cell, so they contribute to the same point in density. They receive the same acceleration because they're just in the same position. So then say, well, that's not very good because if I'm evolving the universe, things collapse. They become denser and denser and denser, so I get more and more, the particles getting smaller and smaller and smaller regions, always more and more concentrated. And at some point, I'll have a lot of particles just within one grid cell, and then they don't receive any gravity anymore, so that doesn't work. So people said, oh, well, what can I do? Well, I'm going to do two things. I'm still going to do this Fourier transform, but then inside one of these grid cells, I'm also going to solve directly this n squared thing. So I get the large forces and the small scale forces. And they call this the particle mesh algorithm, because you do particle and particle mesh.
So I will have two grids.
Now you have only one grid for the large scale. And within each grid cell, we have a lot of particles. There you just do all of the forces by hand.
But it does skyrocket the computation.
What?
It does skyrocket the computation.
Right, but within one grid cell, you will not have all of the particles. You only have, right, if you have a billion particles in calculation, within one grid cell, maybe you only have 10,000. So then it's only 10,000 squared plus the Fourier transform. So it's not as bad. All right. Okay, so the main reason is that so the PM it couldn't deal with large range, it couldn't deal with collapse. So particle collapsing from densities should be able to model the force on these scales. So what do we do? As I mentioned, we compute the force between particles in the same cell using direct summation. So we do this n squared thing, but with a smaller n because it's for each region independently. So that's what it would look like. You have this big mesh where you do the Fourier transform business, and then in this small region here, okay, I should not have drawn a grid because there is no grid. Just in this region here, we do the direct forces between the particles. Because they are close by, so they're in the same pink cell, so they will get all the same force, so we should do something else. So we can add additional regions where we do extra business. Okay, so what is good? Well, speed, again, it's fast, and better than before, we can track collapse, because now we can, in the region where things become dense, I can still calculate gravity correctly because I'm doing this particle business. Right? Problem makes the code a lot more complicated because now I have to have two different calculations, one for the Fourier transform and one for the small. And then the other problem is that how do I decide where to put these additional regions where we do all of this extra action? I have to decide, I have to sort of, how do I know where things are going to become dense? So I have to decide ahead of time, it gets complicated. It's not trivial to decide, it's really not easy at all to decide where things are going to happen, where should I do this extra particle calculation. So that's actually the main limitation. Because if you already know where it's going to be dense, then why are you doing the simulation in the first place? Because you already know the answer. You know where it's going to be dense, so you already know where the galaxies will. Nevertheless, there are still some code using this. Hack is still used a lot. It's a big code used for very large calculation and relatively low resolution. Because it's low resolution, they don't need to put a lot of these meshes, but it's still quite common. Questions? Good. So then we can keep going. And the next level is to do multi-grid and adaptive refinement, and that's a very popular technique. So that's now looking at scope. That's the technique that we can use. So what does that look like? Something like that. I guess you can't really tell what the picture means, but I guess if you make a guess, can you tell me what you think the picture shows?
I would say the massive version of the video, like the formation of the neurophil elements over there.
Yeah.
This is a big map, a big guy is doing something.
So it's not showing the physics bit, it's showing the grid. So what people do here is to say, okay, well, this idea of having one grid and then a smaller grid is good. What if I keep going? What if it gets very dense? I'll add another layer, and another layer, another layer, and I make this automatic. So I make my code decide, okay, here there's a lot of business going on. I'm just going to add another small grid here. And then I keep going, oh, it gets denser and denser, I'm going to add another grid, right? So what's called mesh refinement, so we're refining the mesh, but we're doing this in an adaptive way, so meaning the code is doing this automatically. We're not us deciding beforehand, here's going to be interesting in the grid. We let the code adapt automatically. So what you have here is the big grid, then you have in orange a slightly finer grid, because maybe this region has some interesting stuff going on, and then in blue, the region where it's even smaller grid, and then in pink it's even smaller grid, and then in white it's very, very small, very fine grid, because you want high accuracy there. Right? So these are like multi-level of grids everywhere. So that sounds like a complete nightmare to program, and it actually is. And so now the problem you have is that you can't use the Fourier transform anymore, because Fourier transform work very well if the grid is the same everywhere. If the grid is not uniform, I don't actually have a good algorithm to do Fourier transform efficiently with a computer. Right? We don't know how to do this. So here, what we'll have to do is we're going to use another technique to solve for the grid. We're going to use finite differences. And here we are going to do maybe a small experiment. Can we switch on the light? Okay. Thanks. So I need, how are we going to do this? Okay. So the idea here is that we start with a guess. Right? I'm guessing this is the potential. I don't know what the potential is, but I'm guessing some number everywhere in the grid. And then we're going to say, if this is too far away from the correct solution, I'm going to iterate and correct my solution. And I do this until I'm happy that it's close enough. Okay, that sounds very vague. We're going to try an experiment. I need 7 people to come in front here for experimenting. I'm not biting. 3 more would be ideal. 2 more. 1 more.
Pancho llega, Pri.
Okay, thank you. So what we're going to do is this. So we're going to order by height, and we're going to be looking this way.
By way,
Yeah.
from front to back.
Yeah, let's face this way. Okay. So now what we're going to do is that so the rule is the following: the 2 people at the far end. So let's move all by half a step. The 2 people at the far end, you are not moving. You're at the edge of the universe. We know you are the correct solution. Okay. Now everybody else, you can move left or right by some amount. Let's start moving. You decide left or right how much you want to move, just randomly. Okay. So let's assume this is my initial guess. Right? This is my initial guess for the solution. The correct solution is a straight line. But clearly, my initial guess is not very good. People are not on a straight line. Okay? So now what we're going to do with this algorithm, so the 2 people at the end, you don't move. But what we do in the algorithm is that everybody in the middle, you look at the person in front of you and the person behind you. Okay? And you look at how far they are, and then you decide, okay, I'm going to move to the average position from the 2 people. Does that make sense?
Okay.
So you have the 2 people, don't move now, just stay where you are. So you check the person in front of you, the person behind you, say, okay, maybe the average position is about here. Okay? So when we make a step, you're going to move to this position. Everybody does that. Okay? You ready? So let's all move to where you should go.
I already moved.
Okay, then we'll go back to where you were. Okay, so everybody moves to a new position. Okay, that's a lot better. Now, but it's not quite a straight line still, right? You're still a bit off. You're also still a bit off, so you do the same step again. So we check where your back, the person in front of you, the person behind you is. All good? Let's move. Good. Is it accurate enough? Do we need 1 more step? Yeah. Let's check. Check the neighbors. All right, let's move. Good. We found a solution. Right? We have a very stupid algorithm. Because we're just looking at 2 points, one behind and 1 in front, and we find the correct solution. We're going to try then another random set of positions. All right. Let's try another random. Let's try a different starting point. Or you can do something crazy. Let's everybody goes against the wall, so we get a crazy battle. No, not the endpoint. So let's look at terrible guess. Okay, so are you ready? Check your person in front of you, person behind you, and you move to this position. So you in the middle, you're not going to move. Let's move to the next step. Okay, not a great solution. Let's try again. Check the guys in front and behind. Let's move ahead. And again. And again. And again. And there we go. Right. So we have a that works, right? We're not doing anything clever. We're just checking the points on both sides of us. So if you do this in 3D, you would have to check front, back, left, right, top, bottom. So it's a bit more points. You could take the average of these, but it works. It also works if I do a very terrible guess at the start. So if I put all of you against the wall, it still works. It just takes a lot longer to get to the correct solution. So this is now the solution if I wanted a straight line. So obviously, it's not always a straight line. The potential will have some sort of straight shape. So what I could do instead of giving you just all a straight line, I can attach you to the wall with different different elastics or something that has different strengths that pulls you more against the wall. And then the solution will not be straight anymore because some of you will pull against the wall. So that would be essentially saying we don't want a straight line. We want something where there's more mass in some regions or less mass, but the algorithm will still work. We're going to converge towards the correct solution. Okay? All happy? Makes sense?
That's interesting.
Good.
That's true.
So that works, but it's very slow. So what is the key bit here? We need, right? If we saw this here, I need a very good guess. Otherwise, it's going to take many iterations before everybody is on the correct line. But if I have a good guess, it's going to work quite well. So now, here we did the simple solution thing where we only have one single grid.
How do we know the correct solution? Here you use a straight line, but our potential.
Yeah, so what we have done here is we have done that part here where we put the average of all of these. In reality, you have an extra term that gives you the density field. So that would be me adding some rope against the wall, making you pull. And then that will tell you, okay, I can't really move that far because there's something pulling me. And then that would be sort of an extra term giving you the solution. But you're still minimizing by looking at the neighbors left and right. Okay, now in reality, what you have to do is because we have all of these different grid levels, you have to do this at every level at the same time. So it gets more complicated. Right? We have the very coarse grid and then different levels. So we have to have the solution everywhere and not just at one level. So that gets the same algorithm, but just takes a lot more time. Now the advantage of this is that so here we did a very straight line function, but we can do this with any function. Anything you want to solve, that will always work. It's always very slow, but it always gives you the correct solution. So if you now have a very different theory of the universe where we cannot use a Fourier transform or we cannot use any other approximation, this will work. That's going to be slow. Okay, so what are the pros and cons? Well, we can track collapse because we just add grids wherever something is happening. We can solve any potential, any function we like. Problem is very complex. You have to write this code to do all of these levels, and it gets very tricky. It's not very fast, and it's also not clear how to. It's not always very easy to converge rapidly to the solution. And so here, when I put everybody against the wall, it took many steps. Even though the solution is very easy, it was almost the correct solution, but it took a lot of time. The other case can be crazy if everybody's on a line and someone is very far away. So everybody's almost correct, apart from one person. Then because we take the average, actually people move away from the correct solution before we all move back towards it. So that's very inefficient as well. So it needs to be a good guess everywhere, otherwise it can be take a lot of time before we get where we want. Yeah.
Maybe the answer is obvious, but if we have a more accurate solution, would be be easiest to converge the approximation? Well, I mean, in the example, we have just two correct answers. If I have like, I don't know, six correct answers, and well, the movement will be more easier.
Correct. So the better your guess is, or the better your endpoints are, the better it is. But you have to know something about the problem. It's not always easy to know something that is good enough to make this very, very fast. Yes?
Regarding the Fourier transform, isn't it feasible to make like the Fourier transform for every mesh refinement that we done?
Yes, in principle, but there is no fast algorithm to do this. So Fourier transform, they are very good. So if you just do a normal Fourier transform, so there's this algorithm called the fast Fourier transform, which is what every code always uses. That algorithm only exists if the grid has only one size. We don't know how to do a better way yet. If you have multiple.
All right.
So you would have to do a not fast. You can do a regular Fourier transform, which is not the fast one, but it's not fast.
But can't we do like the fast Fourier transform for every little mesh?
No, because yes, you're thinking about the right thing. The problem is that the detail of what happens in a small batch depends on also of the rest. Gravity is long range. Stuff happening far away has an impact on you. A small one, but it has an impact. So you can't just solve the problem independently. You have to solve all of it at the same time.
It does derange a lot from the.
You will get wrong slightly, but if you want to do something accurate, you can't use that approximation. Questions? Okay, so let's finish off the morning. We're going to talk about tree-based codes, a very different category. And here, the idea is as follows. What we're going to do is that we're not going to do any meshes or anything like that. We're just going to do groups of particles. One way to think about this is that if you want to calculate something here in this room, or say something in the solar system, the fact that there is let's not do this. If you're doing something about the Milky Way, you're trying to evolve the stars in the Milky Way, there is the Andromeda Galaxy not very far. But the Andromeda Galaxy is very far away still. I don't need to worry about every single star in the Andromeda Galaxy influencing every single star in the Milky Way. I can just say, Andromeda is far away, I can just treat the whole thing as a point mass. I can just replace it and say, this is far away, it's just one single mass of the whole thing. I don't have to worry about every single detail of what happened in the galaxy. Okay? So what we're going to do is group particles which are far away for some definition of far away, and consider that they're combined effects. So this particle here, instead of having to calculate the force from every red particle here, we just say, okay, this is far enough. I'm just going to replace all of these red points by one center of mass that contains all of the mass of all of these red points, and just calculate that force. If it's far away, that sounds like it's going to be enough. Of course, if that blob is very close, that's going to be very wrong, right? So we have to find a good definition of far away. So formally, you can write this as being a Taylor expansion. So the potential between two particles DNA, you can Taylor expand around the center of mass. And I don't want to go too much into the detail, but you can write this. You can keep writing this as Taylor expansion, and then summing everything up, and you end up with an expression where the potential at a specific position depends only on what we call the multiple, so the mass of this blob far away. But it could also be not just the mass, maybe you can be tiny more accurate and say, I'm also going to consider the shape of that thing. Because maybe if it's a sphere, or if it's a banana, or if it's a disk, will have a slightly different effect on me, just depending on that. And then it will depend on the derivative of the potential. Okay, so how do we do this in practice? So here are 100 stars in 2 dimensions, because I don't draw in 3D. And we want to calculate all of the forces between all of these particles. Right? That's already expensive enough. So what we first do is we're going to construct a tree. So we're going to start by putting the box around all of the particles. And then every time I have a box which has more than forgot what I chose here, 4 particles, I think. We're going to divide the box into smaller boxes. Okay? So clearly here, whoops. Oh, come on. So clearly here, I have more than 4 particles in my box, so I need to divide it into 4 bits. Here again, each of these 4 regions has more than 4 particles. So, sorry, has more than 3 particles. So I keep going. Here, some of them are done, right? So this region here only has 2 stars, so I don't have to touch this region anymore. This region is more dense, this one as well, so I probably have to keep splitting my regions further and further. Right. It's getting better. And then here, maybe I only have to split these guys here to make the tiny last level. So this is just defining the structure. So you were asking before whether just counting the memory of the particle was enough. In practice, in the code, you also probably construct a tree like that, so the tree itself will contribute to the total code. Okay? So now, why are we doing this? So the idea is I can use these grid and these cells as an idea for how to calculate things which are far enough. Right? It gives me a structure, so I can say, okay, all of these particles here, which happen to be in this cell, are probably far enough from this guy here, and I can use all of them as a single approximation. It gives you a natural, sort of a natural unit of approximation for the distances. So what do? What's the algorithm? We build a tree, which we just did. Then we calculate for each of these cells the center of mass, or the shape, the multiple, we call the multiples. And then what we do finally is that for each particle, we calculate, is this cell far enough? If it's far enough, I just use the center of mass. If it's not far enough, I go to the next level in my grid. Okay? So, let's look at one single particle. So here's again exactly the same cell. I'm interested in the particle on the bottom left here. Okay, I'm going to calculate all of the forces. So what I'm going to do, I'm going to start at this level here, and I say, is this total box here far enough? If it is far enough, I'm going to replace this calculation here by just the center of mass, which is probably going to be somewhere in the middle here. And that's it. I can stop here. I don't have to calculate all of these extra forces. I just have one force for this quarter of the universe. Big speed up. You can say, oh, is this box here far enough? And is this box here far enough? Problem. This box here is definitely not far enough because I'm inside that box. So then what you do is that you go to the next level and you say, okay, is this box here far enough? Right? And if yes, you use the center of mass, which is going to be, I don't know, probably around here. And if not, you have to go to the next level.
What's the condition to be far enough?
Good question. We'll come to this in a second. Yes?
Couldn't we, instead of using the next level of the tree, use another multiple, like second?
Yeah, so you could say I can use a higher order multiple in my Taylor expansion. Yes, that could be the other thing, but maybe so typically people fix the multiple order. So they fix the order in the Taylor expansion and then they use the distance criteria. They don't do it the other way around. It's more efficient this way because going to very, very high multiple doesn't gain you as much as just choosing a good choice for far enough. So if I now represent this in terms of how the number of calculations I have to do, if I do my calculation where every star has to interact with every star, then this star here has to calculate all of these red lines. But if I use this approximation saying this box is far enough, then I only have to do these green interactions here. And okay, these guys are in the same box, so then there's no chance to be far enough. They're in the same box, I have to calculate it directly. Right, so instead of doing 99 calculations here, I only have 1, 2, 3, 4, 5, 6, 7. So I've gained an order of magnitude. If I make my tree deeper and deeper, it gets better and better. Yes?
There's a star just
You mean these two here?
to dab into the vein. It's something outside. It's just on the
Yes.
center of the green.
Maybe I didn't. Oh, this one?
No.
This one?
Uh,
This one?
Left down, left down, left down, left down. There.
Yes.
It's outside the circle.
or everything is.
Okay, yes. No, okay. Well, first of all, I drawing this by hand, so might not be very accurate. But yes, so the idea, so you could ask the question, is this really far enough? Because this one is definitely, but so what we try to do is we say, I'm going to replace this entire box here by that approximation, and we decide that this doesn't matter. You could say maybe that's not good enough. So maybe you would say, oh, I need to cut that box here finer to get this more accurate.
But the main star is interacting with the one that has been discarded.
It's not been discarded, it's included in this cube here. Right, so we don't, so all of these green stars here, they are all included into that center of mass. Okay? So we don't, with the mass, we introduce the total of all of the mass, but maybe not exactly the position where they are. Okay, so you were asking how do we know it's far enough? So we said it's a Taylor expansion. So what we can do, when you have a Taylor expansion, you can verify that all of the extra terms contribute less to what you have than what you already stopped. And if you do the Taylor expansion, you can see that actually what is the order of the approximation is essentially the size of the cell of this square I was drawing divided by the distance to that thing. So I have the size of the cell and then the distance to that cell. And then what people do is that, okay, so if they define this as, they call this an angle, because you could say, how big, so if I'm like looking at the sky, let's say calculating gravity forces, how big is that area on the sky? So what is the angle that this Andromeda galaxy is doing on the sky? If that angle is very small, it means it's either far away or that doesn't contribute much. So I can say that angle is small, I can use the approximation. If the angle is very large, probably something very close by, so I have to split it into smaller pieces. Okay? So people typically use a value of 0.7 because experimentally it worked very well by doing testing whether it's accurate enough. So you define the distance in this way. Okay, so since I did pros and cons before, so what a tree was good for? Well, they can track collapse because they can do, we just add more and more levels in this tree when things get very close by, we just split it into smaller pieces. The other thing is very easy to implement, easy to write it. It's very easy to write the code. It's actually also very easy to write it to work on a big cluster, but that's a separate discussion. Other things which are not great, well, it's not easy to do something that is not Newtonian gravity. So if you were to worry about some other forces, it's not easy because this whole Taylor expansion thing that only depends on distance, that only works very well for Newton. And then algorithmically you can show that it's not optimal, but that's a small detail. Yes, there was a question on that.
Since these stars are moving, of course, this tree mesh is changing at time.
Yeah.
What's the main difference between this and adaptive mesh? Since both are like changing.
Yeah. So here the difference is that you don't use the mesh to calculate this potential using the line of people. You use the tree to decide whether the gravity forces are calculated. So here we're not solving the potential on the mesh using this technique of taking the average of both sides. We're directly doing this approximation of the Taylor expansion of the forces. But you're right that the structure of having more and more levels where it gets dense, the two look very similar visually. You have more cells where it gets dense. But then what you do once you've constructed the tree is slightly different. Okay, and just to finish off, the last method, which is very similar, is a fast multiple method. And then so the idea here is to say, okay, what we did looks very good, but we can do a tiny bit better. So if you look at these two here, so we looked at this case before, and we looked at this star, and which other cells it's interacting with. Now if I take the other star, which is in the same cell, it's also interacting with the exact same list of regions, right? So it's interacting with this guy like this one with this one, and so on, right? The same exact list of forces. So instead of doing this twice, what I could do is I could calculate the force not on each of these stars, but on the center of mass here, and then just distribute the forces directly to the particles. And then I only calculate, that means that for both particles here, I only have to calculate once this whole thing, So make the thing even twice as fast. Okay, it's conceptually a bit more complex because then you have to think about how you can approximate things, but those two are receiving pretty much the same force. They're interacting with the same list of people with pretty much the same distances. So it sounds like I can do it only once, then just add a tiny correction. That sounds very hand-wavy. What you are doing now, instead of doing a Taylor expansion around here, you're also doing a Taylor expansion right here. So you're doing a Taylor expansion of both sides of the equation, then combining the terms. And again, I'm saying this in a very hand-wavy way, but you can demonstrate that this is the most efficient way. It's the least number of operations to do to calculate all of the forces between these particles. So we expand the Taylor series on both sides. It is much more complex to write a code that does this, but it's also faster. And then the advantage it also has is because now it's symmetric. So because we're doing a Taylor expansion on both sides, it's also conserving momentum. The other one, all of the other methods do not conserve momentum. This one is a tiny advantage, but it doesn't actually matter that much. And so the code we're using, we used yesterday, we're using this afternoon, uses this method behind to calculate time. So you can get cosmological boxes like that. Right, so we're reaching lunchtime. Are there any questions before? I'll just say a few words about this afternoon stuff.
Is there any way to calculate the maximum number of cells or the levels to get the maximum evidence from the method?
Can you repeat the question? So you want a maximum number of cells?
Or levels?
Yeah. So that will depend on, so here in my example, I decided to, every time I have more than 3 stars, I make a new level of cells. That's a parameter I can choose. If I've decided to make a new level every 5, then my tree will be more shallow. So different code, then it will depend a bit. There is no fixed answer as to how you should do this. Different codes have different criteria to stop creating new levels. Some codes go all the way down to 1 star per cell. And in some codes, like the one we use with the one I use, we stop at about 200. But then we say, anyway, it doesn't matter because if I have a cell with 200 particles, my close-by criterion will still make me do all of the interactions anyway. So I may not want to construct all of the small cells. There is no point. But it's more of a choice of when you start coding the whole thing. It doesn't make a big difference in practice on speed or accuracy. It's more of a design choice. Okay, so we did all of that. I'm going to skip ahead a bit because then I'm going to come back to some of the technical. So one thing we didn't talk about was initial condition, how we start a simulation in cosmology setting, and how we choose the time step. We can talk about this a bit tomorrow morning, but I'll skip ahead just about what we want to talk about for this afternoon. So this afternoon, what we're going to do is going to run some. So we used the code yesterday, so you already compiled the code, you run it on a simple setup in principle. What we're going to do today is we're going to run a slightly more complex setup. We're going to run actual cosmological simulation, and we're going to measure some properties. So some people yesterday were asking, how do we compare the simulation to the data? But of course, we're not just looking at the maps and say, oh, that looks the same. You have to do some more serious statistical analysis of this. So one of the tools you can use would be to look at something, the halo mass function. So in some of these models, what you have is that you form halos. So the first thing you can do, and the simplest thing you can do, is just count. In one region of the universe, how many halos of a given mass do I have? And if I change my cosmology, or if I change something in my physics, probably, well, not just probably, in practice, the number of halos of a given mass per unit volume will be different. So if I go now and measure it in the universe, if I can measure that same thing in the universe, which is not easy to do for this one, I can compare and rule out models. And say this model doesn't work because it has too many big halos, or too few big halos, or something like that. Then the other tool, which is often used, is the power spectrum. So power spectrum here is just fancy word for saying the Fourier transform of the density field. And again, so that's very easy to do this simulation. You have the density grid. You can take the Fourier transform of that, and that tells you, and were saying before, we have all of this. What does the Fourier transform mean here? Just the amplitude of each of the waves that are in the box. In the data, I can do the same thing. I can take my map of all of my galaxies and then try to do a Fourier transform of that thing to tell me what is the power spectrum, the density fluctuation power spectrum. Now, in the data is always much, in the simulation it's very easy because it's a cube and Fourier transform is super easy to do. In the data, it's going to be more difficult because maybe there's a region of sky you can't see, so then you have a hole here. Right? Or the data, the universe is not in a cube. You are in the center, you're looking at things that will look like, will have a strange shape. So in the data, it's very complicated, but it can be done, and then you can start comparing models. For instance, here you have some data points in black, and then you have here different models of universe where I think in this one, they change the mass of the neutrino particle. So if you make your neutrino particle much more massive, then it doesn't fit the data anymore, which give you some constraints saying the neutrino, which we don't know what mass the neutrino is. People on ground experiments have not yet measured it. But we can tell people that do experiments cannot be that big, otherwise the universe is broken. Okay? But so today what we're going to do with the simulation is that we're going to be running a cosmological calculation and then measure the power spectrum of the results. And I think that's what I have for today. Yes, that's this has to do with the measure power spectrum. Any questions on this morning or anything? No? Then I'll see you this afternoon.